Welcome back to the Deep Dive. Today, we are tackling some really big questions. What is time? How did everything begin?
Yeah, the big ones.
We're looking at Stephen Hawking's The Universe, in a nutshell from 2001. Specifically, how he took Einstein's groundwork and, well, ran with it into some pretty mind-bending places.
Absolutely. We're basically tracing how Einstein's twin revolutions back in 1905, general relativity and quantum theory, forced us to completely rethink, well, everything. Space, time, even predictability itself.
But first things first, we have to talk about what Einstein dismantled, right? This idea of a single universal time.
Exactly. And to do that, he had to get rid of this concept called the ether.
The ether. This, like, invisible goo-filling space that everyone assumed light waves travel through.
Sort of like sound through air, yeah. And if it existed, the speed of light should change depending on how you're moving through it. Faster toward the source, slower away. Makes sense, right?
Seems logical. But then came that experiment in Cleveland, Ohio. Mills and Morley.
That's the one, 1887. They were trying to measure these tiny differences in light speed as the Earth moved through the supposed ether. Nothing. Nada. They couldn't detect any difference at all, which basically meant the ether, well, it wasn't needed.
Okay, so no ether. And that's what let Einstein propose his really radical idea for special relativity.
Precisely. He just stated, the speed of light is the same for all observers who are moving freely. Doesn't matter how fast you're going or in what direction. The cosmic speed limit is constant.
And the implication of that, if speed is constant, time can't be.
You got it. Absolute universal time goes out the window. Instead, everyone gets their own personal time.
Personal time, okay.
Yeah, how fast time passes for you depends on how fast you're moving relative to someone else. And we've actually proved this.
With the clocks, right?
Yeah.
Flying them around the world.
That's a famous one. They flew super accurate atomic clocks in opposite directions. The clock going east, moving faster relative to someone on the ground. You know, because of Earth's rotation, it actually recorded slightly less time had passed.
Wow. It's tiny, but it's real. Time is relative.
It is. And that's our jumping off point. Understanding that time isn't fixed is crucial to grasp, well, the Big Bang, black holes, all the weirdness that follows.
So where do we go from special relativity, which only deals with constant motion, right?
Okay, move to the big one. General relativity, or G.R. Einstein's 1915 masterpiece. See, Newton's gravity had this problem. It acted instantly across space.
Which special relativity said was impossible because nothing travels faster than light.
Exactly. So GR reimagined gravity. It's not a force pulling things together across empty space. Instead, mass and energy actually warp and curve space-time itself. Space-time isn't just a stage, it's an active player.
Right, the rubber sheet analogy. Though, people always say don't take it too literally.
Yeah, it's just a visual aid. But the idea is a big mass like a star creates a dip in the sheet. A planet rolling nearby isn't being pulled by the star. It's just following the curve in the sheet created by the star.
So the path is dictated by the geometry of space-time.
That's gravity. But here's the twist. GR, this incredibly successful theory, actually predicts its own downfall.
How so?
When you apply it to situations with extreme gravity and density, like tracing the universe back to the very beginning, or looking inside a collapsing star, GR predicts points where density becomes infinite. Singularities.
Places where the laws of physics just stop working.
Precisely. The two most famous examples are the center of a black hole and the very beginning of the universe in the Big Bang model.
And Hawking, along with Penrose, used GR to show that the Big Bang singularity wasn't just a maybe, it was a necessity.
Under the rules of GR, yes. If the early universe was dense enough and observations show it was incredibly dense, then time must have had a beginning.
How dense are we talking? You mentioned some figures.
Yeah. The minimum needed for their proof was about 10 tons per cubic inch. But the estimates from the cosmic microwave background, they suggest something truly astronomical. Maybe one followed by like 72 zeros. Tons per cubic inch.
I can't even picture that.
It's insane. Basically, a sugar cube of that stuff would outweigh, all the mountains on Earth combined. So, GR says, point of infinite density, definite beginning of time.
Okay, but if the theory breaks down at that beginning point, that's a problem.
A huge problem. It tells us GR isn't the full story. We need something else to describe that initial moment. And that brings us to the other revolution Einstein started. Quantum mechanics.
Quantum mechanics, QM. The theory of the very small and the theory that introduced uncertainty, right? Much to Einstein's annoyance.
That's the one. God does not play dice, as he famously said. QM destroyed that old idea of classical determinism, Laplace's demon. If you knew the position and speed of everything, you could predict the future perfectly.
QM says you can't know both position and speed precisely at the same time. The uncertainty principle?
Right, but it didn't lead to complete randomness either. A different kind of determinism survived. We can't predict exactly where a particle will be, but we can predict its state, its wave function, which is basically a cloud of probabilities using the Schrödinger equation. We can predict the odds perfectly.
Okay, so there's still some predictability. But then, black holes mess things up again.
They really do. Remember, black holes are regions where gravity is so strong, nothing escapes, not even light. And they're simple objects defined only by their mass, their spin, and their electric charge. The no-hair theorem.
Meaning they erase all the details about whatever collapsed to form them. Information loss, even before quantum mechanics comes in.
Exactly. But QM adds another layer. It tells us that even seemingly empty space, the vacuum, isn't truly empty. It's fizzing with activity.
Vacuum fluctuations, little pairs of particles popping into and out of existence.
Virtual particles, yeah. They appear as a particle-antiparticle pair, exist for a fraction of a second, and then annihilate each other, usually.
But near a black hole.
Near the event horizon, the point of no return, something different can happen. A virtual pair pops into existence. One particle might have negative energy, the other positive.
Negative energy, how does that work?
It's a quantum thing. Think of it like borrowing energy from the vacuum. Anyway, if the negative energy particle falls into the black hole actually loses a tiny bit of mass. EMC squared, right? Mass and energy are equivalent.
Okay, and the other particle?
The positive energy partner escapes. It becomes a real particle flying away from the black hole. And we can detect this escaping energy as heat, as thermal radiation. That's Hawking radiation.
So black holes aren't truly black. They glow faintly and evaporate over immense timescales.
Correct. But here's the killer blow to determinism. That escaping particle carries energy away, but it seems to carry no information about what fell into the black hole originally, or even about its partner that fell in.
Why is that so bad for determinism?
Because if you, as an outside observer, see that radiated particle, you can't trace its quantum state, its wave function, back through time to figure out its origin. The information contained in whatever made the black hole and in the partner particle seems to be utterly lost when the black hole evaporates completely.
It doesn't just get scrambled, it's gone.
It appears to be gone from our universe, which means our ability to predict the future using the wave function, it breaks down. If information can be destroyed, the quantum determinism we thought we had evaporates too. Fundamentally, we can't be sure about the future.
Wow, okay, so GR breaks down at the beginning, and QM seems to break down with evaporating black holes. We desperately need a theory that joins them.
The theory of everything, or TOE, that's the holy grail. And the best contender we have right now is something called M theory.
M theory. That's one with extra dimensions, right?
Yeah, it seems to require 10 or 11 dimensions in total. Most of them, the idea is they're curled up incredibly small, so we don't experience them directly.
And how does M theory help with the beginning of the universe, the singularity problem?
It uses a mathematical technique, a really clever one, involving imaginary time.
Imaginary time, like using I, the square root of -1. That sounds completely abstract.
It is abstract, a mathematical trick, but it has a profound consequence. When you switch to imaginary time in the equations describing the universe, the time dimension stops behaving like, well, time, this relentless forward march. Instead, it acts just like another dimension of space.
So time gets a shape, like space has shape.
Exactly. In imaginary time, the universe's history isn't a line starting at the Big Bang. It can be visualized as a surface. And this led Hawking and Jim Hartle to the no-boundary proposal.
The universe in a nutshell idea.
That's the one. Their proposal is that the history of the universe, viewed in imaginary time, is a finite, closed surface. Think of the surface of the Earth. It's finite in area, but it has no edge, no boundary, no starting or ending point you can fall off.
So in imaginary time, the universe has no beginning singularity, no edge.
Correct. It's completely self-contained. It just is. Which means you don't need anything outside the universe to, kick it off or create it. No external cause required.
That's philosophically huge. The universe explains itself.
In this picture, yes. Now, this ties into another quantum idea from Richard Feynman, the concept of multiple histories, or sum over histories.
The universe explores all possible paths, like a quantum particle.
Sort of. The idea is the universe doesn't have just one single history. It has every possible history simultaneously, each with a certain probability. We just happen to observe the one we're in.
But why this one? Out of all possibilities.
That's where the sometimes controversial anthropic principle comes in.
The idea that the universe must be suitable for life, otherwise we wouldn't be here to observe it.
Basically, yeah. It acts like a selection filter. M-theory might allow for universes with, say, 9 spatial dimensions, but calculations show that in universes with more than 3 large space dimensions, gravity wouldn't allow stable orbits. Planets would either spiral into their star or fly off into space.
No stable planets, no life like us. So we naturally find ourselves in a three-dimensional one.
It seems plausible. And the most probable history in imaginary time, according to the no-boundary calculations, happens to correspond to a universe that in real time underwent a period of rapid accelerating expansion right at the beginning.
Inflation.
Exactly. Inflation naturally explains why the universe is so smooth and uniform on large scales today. It stretched out all the initial wrinkles, and it elegantly solves the energy problem too.
How's that?
Inflation effectively borrows energy from the gravitational field. Matter has positive energy, but the gravitational field has negative energy. In an inflationary universe, these can perfectly balance out, meaning the total energy of the universe could be exactly zero.
Created from nothing, because the total book's balance.
A universe for free, as Alan Guth put it.
Okay, so we have this self-contained, possibly zero-energy universe born from quantum fuzziness. What about, can we mess with time itself? Time travel.
The fun stuff. Well, GR does allow for theoretical possibilities. Solutions involving things like rotating black holes or wormholes tunnels through space-time, or maybe 2 cosmic strings moving past each other at near light speed. These could potentially create closed loops in time.
Allowing travel to the past.
In theory. But Hawking was skeptical. He proposed the chronology protection conjecture. Basically, that the laws of physics themselves conspire to prevent macroscopic time travel.
How would physics protect the past? What's the mechanism?
Well, building any kind of stable, traversable wormhole or time machine seems to require exotic matter with negative energy density, something that pushes space-time apart, anti-gravity, essentially.
If that even exists?
Quantum mechanics allows for tiny, fleeting amounts of negative energy density, those vacuum fluctuations again. But the conjecture argues if you tried to stabilize a wormhole big enough for, say, a person, the quantum effects would run wild. Virtual particles looping through the time machine would reinforce each other.
Building up energy.
Infinitely so. Right at the entrance to the time travel horizon, the energy density would become infinite, basically creating a singularity that would destroy the wormhole, or at least prevent anything macroscopic from passing through.
So quantum jitters slam the door shut on traveling back in time.
That's the idea. Physics has a built-in security system for causality.
Okay, no easy trips to see the dinosaurs.
Yeah.
Let's push even further into the speculative realm then. Brain worlds. What's that about?
This comes directly out of M-theory and those extra dimensions. The idea is maybe our entire universe, the 4 dimensions we know, 3 space plus 1 time, is actually just a surface, a brain, floating within a higher dimensional space called the bulk.
Like a sheet of paper in a 3D room.
Kind of. And the idea is that all the particles and forces we know, electromagnetism, nuclear forces, are stuck on this brain. They can't leave it.
But gravity.
Gravity, being the curvature of space-time itself, might be different. It could potentially leak out from our brain into the higher dimensional bulk.
And that could explain why gravity seems so much weaker than the other forces. Because it's diluted by spreading into extra dimensions.
That's one fascinating possibility, yes. It could also potentially explain dark matter. Imagine there's another brain, a shadow brain, parallel to ours but hidden in the bulk. We couldn't see its matter or light because those forces are stuck on its brain, but its gravity could leak out and affect our brain.
So dark matter wouldn't be some weird particle in our universe, but just the gravitational pull of ordinary matter on another nearby universe?
It's a possible explanation, and it connects to an even stranger idea: holography.
Like the holograms on credit cards?
Sort of, but cosmically. The holographic principle suggests that all the information contained within a volume of space, say a 3D sphere, can actually be fully described by physics just on the 2D surface of that sphere.
The information for the inside is encoded on the outside.
That's the mind-bending idea. Maybe our 4D spacetime's just a holographic projection of physical processes happening on some boundary surface in a higher dimension. We might be the shadows.
Okay. My brain hurts a little now. From the Big Bang to cosmic holograms. Let's maybe bring it back to something a bit more tangible. complexity and the future.
Right. Even with all this cosmology, there's this fundamental limit we keep hitting, the speed of light. And that limit doesn't just constrain spaceships, it constrains the speed of information processing, the evolution of complexity itself.
And the sources talk about how complexity has been growing, but like exponentially.
Yeah, it's striking. Biological complexity, measured roughly by the information in DNA, evolved incredibly slowly for billions of years, maybe adding one bit of information every 100 years or so.
It's a snail's pace.
Then came language, culture, writing, and suddenly things took off.
Yeah.
And now we have electronic complexity Moore's law, computers doubling in power roughly every 18 months. It's an exponential explosion.
Which suggests the future might not look like, the static universe of Star Trek where things are advanced but fundamentally similar.
Hawking certainly didn't think so. He speculated that genetic engineering, maybe combined with electronic enhancements, could allow humans to overcome current biological limitations, like the size of our brains being limited by the birth canal.
Leading to a future species very different from us.
Potentially unrecognizable. The only ultimate physical constraint on the speed and complexity of processing information, whether it's biological or electronic, is the speed of light itself.
So we've gone from Einstein breaking absolute time through quantum uncertainty and black holes to this self-contained nutshell universe predicted by M-theory and imaginary time. And maybe we're holograms on a brain.
It's quite a journey, unpacking how space and time aren't just a backdrop, but dynamic players in a quantum game. And that game seems to be accelerating in complexity.
Which leads us to our final thought for you to ponder. The source material points out that we, Homo sapiens, have only been around for maybe 2 million years. The universe is about 15 billion years old. That's a tiny fraction.
A cosmic blink of an eye.
And considering this accelerating complexity, Hawking notes it's not even clear that our kind of intelligence offers a huge long-term survival advantage. Bacteria have done incredibly well for billions of years without pondering quantum gravity, and they might well outlast us.
They're certainly more resilient in many ways.
So the question to leave you with is this. Given this incredibly rapid, maybe even runaway, increase in complexity happening right now, what does that imply about where the universe is heading? Is there an ultimate goal to all this complexification, or is it just happening, something to think about from inside the nutshell?